So we continue with this lecture on basic designs, and let us introduce now a bit more sophisticated ideas. So the first one is the idea of non-orthogonal designs. So let's say that you are looking at the effect of two different so you are interested in the growth of tomatoes, and you are interested in the application of two treatments that are using different concentrations of a chemical growth regulator, and you will also include the control spray. So you have three treatments. So you have the two concentrations plus the control. So you have three possible treatments, and because you are given a small land, and in this small land there might be a gradient of fertility because a part of it is more in the shadow, or a part of it is closer to a water source or whatever. So you want to avoid this possible gradient, so you divide the land in three pieces, so 3 columns, 3 rows, and in each one of the subplots you apply a treatment. So you have in row 1 you would have ABC, in row B you will have CAB, and in row 3 BCA, and the same for the columns. So rows and columns are the different regions of the land, and then the treatment is at this ABC, that A and B are the two different sprays, and then C is the control, and then these numbers here are the average of the size of the tomatoes in whatever units and however you measure them for that sub-region. So for instance here we have for this subplot the average is 3.72, and for this subplot the average is 3.39, and so on. So it is this kind of designs are called Latin squares. So Latin squares, you have two blocking factors. So actually the rows and columns, they may affect the results. So that is why you want to estimate them, but those are of no interest. So you're not interested in this treatment is particularly good for this row because that is your particular row. Actually, that is the difference between factors and blocks. So factors are variables for which you may be interested in the interaction of that variable with other variables, while blocks you are not interested in their interaction. Okay, so if you look at each row, it has only one combination of treatment, so the treatment is applied only once. So you have A, B, C, C, A, B, so the treatments are applied only once, and the same happens for the columns. And this is a Sudoku. This is a Sudoku in which all treatments appear in all rows and in all columns, and they cannot be repeated. Okay, so that kind of design is called a Latin square. Okay, so we already know how to estimate the contribution of the rows, the columns, and the treatment. So for instance, for the treatments we compute the overall mean, and then we compute the mean of all tomatoes receiving treatment A, and we subtract the overall mean. That is what we learned in the previous block of the lecture. And the same for the rows. So if I want to see what is the contribution of this row, I compute the average of the row and subtract the mean, the overall mean. So those we said those are true for balanced designs. Okay, but I can pose this problem differently, and then I may try to estimate what is the contribution of the mean, the rows and the columns and the treatments in this way by solving an equation system. So for instance, this one is 3.72, but this 3.72 has to be the overall mean plus the contribution of the first row plus the contribution of the first column plus the contribution of treatment A plus some noise, but here we have the average, so there is no noise. Okay, so this is what I have written here. So this 3.72 is the overall mean plus the contribution of the first row plus the contribution of the first column plus the contribution of the treatment A, and then the 3.39, it is the same, but now we have column 2 and treatment B, and you can do the same for all the others. So now you have an equation system, and you may remind your algebra classes, so you can write this in a matrix form. So you have 9 measurements, so you have 9 equations, and let's see how many unknowns we have. So we have 1, that is the overall mean, we have 3 rows, 3 columns and 3 treatments, so you have 10 unknowns, and this is the system matrix. So to get this 372, you would have 1 times mu plus 1 times R1 plus 1 times C1 plus 1 times TA, and then that is equal to 372, and the same for the others. So what we have written are the equations, but now in a matrix form. And yeah, we have counted that we have 9 equations and 10 unknowns. That doesn't sound like sensible, but now we have not introduced yet the constraints. So we know that we don't need to estimate R3, because if you give me R1 and R2, I can calculate R3 as this thing, because the addition of the 3 has to be 0. And the same happens with column 3 and with the treatment C. So I can eliminate. So whenever I have here column 3, for instance, instead of column 3, I can write this thing, minus C1 minus C2, and the same for all the others that disappear, so TC or R3. So if I now do that, then this would be my equation system. So I still have 9 equations. Now my unknowns do not include R3, C3 or TC, because I can compute them from these ones. And now the matrix looks more ugly, because we have all these minus ones, but still the way to compute is the same. So for instance, this 372 would be mu plus R1 plus C1 plus TA, and then for instance here in this one we had C3 and TC, so we see that it is mu plus R1, and then we had C3, but then we have to subtract C1 and C2, and we had TC, and we have to subtract TA and TB, and well, all the others are the same. So now we have 7 unknowns and we have 9 equations, so that is something that we can do. And this problem is said to be orthogonal. So orthogonal means that if you take the columns corresponding to each one of the factors, or to each one of the levels, so we have mu, we have R1, we have R2, and so on. And now we compute, for instance, the inner product between these two vectors. So the inner product between these two is 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 0, so on. You add all these multiplications and what you get is 0. So mu times R1 is 0, mu times R2 is also 0, mu times C1 is 0, mu times C2 is also 0. So all of them are 0, except as long as you are in a different factor. So R1 times R2 is not 0. okay, but this is not considered. So it is different factors, so mu with R, mu with C, R with C, C with T, all these are 0. So the fact that they are 0 is said that this matrix is orthogonal, the design is orthogonal, or it is balanced. Okay, but now the director of your institute comes and says, okay, I like a lot the experiment you are doing with the tomatoes. I'll give you a little bit more land so that you can have more samples. And then you have an extra row, and in this extra row, these are the values that you get. And okay, so now you come to estimate your parameters, and it turns out that C and T are no longer orthogonal, so you have lost orthogonality. And well, what does it mean? Rows and treatments. It was rows and treatments, or columns and treatments. So columns and treatments, they are not orthogonal. What does it mean in practice? It means that there are some columns in which the number of treatments is not the same. So for instance, here you have seen C twice but A and B only once, and here you have seen B twice but A and C only once, and the same here. And here you have seen C twice, but here it is B twice, so they are not orthogonal to each other. So you have not the same number of treatments in all the columns. So we said that at the beginning of this lecture, that they don't need to be orthogonal, or the experiments don't need to be balanced. It is better if they're balanced, but they don't need to. So this non-orthogonality translates into the design. This is the design matrix. So into design matrices that are not orthogonal, and that has an important consequence. The important consequence is that we can no longer use the formulas that we know for calculating the treatments effects, the row and columns effects. So what we did before was the average of the treatments minus the overall mean, or the average of the rows minus the overall mean. So we cannot use those formulas anymore. Before, how we were doing also, it didn't matter actually the way we did, but the way we did was we first estimated the overall mean, then with the overall mean we calculated the main effects of the different parameters, and then we calculated the effects of the interactions. So all this procedure in which you first you calculate something and then something else. For instance, now for non-orthogonal designs, you cannot do it in this way. You have to solve all of them at the same time using these least squares. And if you follow any sequential procedure, depending on which order you fit your parameters, you will get some results or others. So it is not extremely different results, but estimates of your main effects and so on, but they're not the same. So you have to solve all of them at the same time. And with this we can go into the concept of covariates and contrast. So let's say that the growth of the tomatoes, they may also change with the ambient temperature. So the ambient temperature is something that you cannot control, but you can measure. So you can accompany each one of these means with the ambient temperature for each one of them. So now when I try to solve my equation system, all I have to do is you can see that I'm mixing here. I have an overall mean, and then the contribution of some discrete variables I have discrete contributions for treatment A, B, and C. So this is a discrete variable but the temperature is a continuous variable. So in the same model you have discrete factors and continuous factors. These are called mixed models. So and how many degrees of freedom do you need for the mixed model? For the continuous factor, you need only one, the beta that goes in front of it. So now beta is an unknown, and what I have to do is to expand my system equation with something, my system matrix with the temperature. So this is the new thing, and we already see a difference between the nature of this design. So in the previous design, all this part of the matrix only depended on what is your arrangement of rows, columns, and treatments, and you know that before doing the experiment. So the system matrix is known before doing the experiment, but if you include covariates, this column here depends on the temperature, and you only know that after doing the experiment. So if you have covariates, the system matrix depends, you have to wait until or a part of the system matrix you have to wait to do the experiment, because it is unknown at the moment of design, but the other part, this one, is known before doing the experiment. Okay, so contrast. What are contrasts? So let's say that remind that our simplified parameter vector, so the one that we have eliminated the redundancies, is this one. So we don't have R3, we don't have C3 or TC. And let's say that we want to know if there is a difference between the sprays. So we have treatment A and treatment B. If there is no difference, this sum has to, or this subtraction has to be 0. And I can write that in this way. So I can write this is a vector transpose times my unknown, my parameter vector, and then this product has to be 0. So in general, a contrast is a test in which I have a vector that is the one defining the contrast times the vector of parameters is equal 0. And this C has to, if it adapts to 0, then it is said to be a contrast. Okay, so it is called a contrast. So I can compute R1 minus R2, R2 minus R3, and all of them. So this is a contrast. This is not a contrast because you see that the sum is not 0. Okay, so and at the end, all these tests I can do them, and I have an F associated to each one of these tests, and so on. Okay, so what is a regression design? So regression design is somehow related to covariates. So let's say that I have this experiment in which I have 10 possible doses. I want to see what is the response of males and females to these 10 different doses, and this is what I get. So I see that there are differences between both. So what I say is that my observation is an overall mean plus something that depends on the dose plus something that depends on the sex plus something that depends on the interaction between the two. If you count the number of degrees of freedom that you need to estimate this model, okay, so we have 9 degrees of freedom for the dose because I have 10 doses, 1 degree of freedom for the sex, so I have 10 here, and then 9 times 1, that is 9 for the interactions. So I have 19 degrees of freedom. So I have to estimate 19 parameters, and 19 parameters, so I can do it, I can analyze it in this way, but I will need many animals because I need to estimate 19 parameters. Okay, I can say, okay, my model will be different. My model will be, there will be a saturation value. This is Y max, and then this kind of functions, they are called sigmoids, and you can do it with an hyperbolic tangent, and then you put something inside that depends on the sex, and that depends on those, and the dose may depend on that there is a parenthesis missing here. So this beta is beta plus beta sex, and then multiplied by D. And so you have a slope. So how many parameters do you have? So you have 1 here, 2, 3, 4, and 5. So I only have 5 degrees of freedom. I only need to estimate 5 degrees of freedom. So I agree that this is a non-linear function, that it looks complicated, but computers can deal with non-linear functions. There are numerical ways to do that. But the important thing here is that I need many fewer animals, because here I have to estimate 19 parameters, here I have to estimate only 5. And there is another important effect, that is the best sampling times for the doses do not need necessarily to be equally spaced. So I don't need any more 10 equally spaced doses, but the optimal design, and I can do this before doing the experiment. Remind your system matrix, you can design it before doing the experiment. So the system matrix, the best sampling doses, I can distribute them all over the curve, and they don't need to be equally spaced. Okay, so least squares have appeared as the way to solve for non-orthogonal designs. Okay, so what is least squares? Least squares is a bit complicated thing, but actually mathematically it's not so complicated, but it looks like. Okay, so this is our model. So our model is our observations is a matrix times a vector of parameters plus some noise. And if we assume that the noise has zero mean, so the expectation of the noise is zero, is a zero vector, and it has covariance, this is the identity matrix, then the expected value of this is simply A times theta. Theta is the vector of parameters, and because the noise has zero mean, it has disappeared from the expectation. And the sum of squares we can compute as this thing here. So it is our observation minus A theta transpose, this is a vector, and then this transpose times this one. So all this together is a scalar. And then the minimizer of this sum of squares is what is the best theta that minimizes this sum of squares, and it is this one. Okay, so this one is, it looks complicated, but it is not so much. So you take the system matrix, transpose it, multiply by A, now compute the inverse, and then multiply again by A transpose, and then the vector of observations. So in this example that we had with the tomatoes, and this one that was non-orthogonal, this one here, all we have to do is just this A transpose A minus 1, and then A transpose this vector. So we solve for all of them at the same time. And interestingly, we can characterize what is the variability associated to this vector of parameters. So we have to estimate what is the contribution of the treatments, what are the contributions of the rows, the columns, and those are random variables in themselves, because if I repeat the experiment, I will have similar values but not exactly the same, and then that will translate into slightly different estimates of the contribution of the treatments, the rows, the columns, and so on. So I can characterize what is the variability of these parameters, and the variability is this one. So it is related to A transpose A and the inverse of A transpose A. So yeah, so we can make this reasonings about the singular values of the matrix A and so on. But what I want to convey with all this analysis is that experimental design, before doing the experiment, is a way to construct the matrix A such that A transpose A has a determinant that is as large as possible, and if the determinant of A transpose A is as large as possible, then because you have an inverse here, you will be dividing by big numbers. So now if you divide by big numbers, you will have little variability of your estimates, and or you may concentrate in one of the components and say, okay, I want to estimate the treatments with as much accuracy as I can, and then you would go to this one and you would say, okay, this particular value has to be very small. So experimental design is a way to construct the matrix A, and this idea will appear later in the next video, where we'll show a program to compute all these kind of things, and we will see that what we are designing are the properties of the matrix A, and then we can do the same for contrast. So for contrast that have this kind of formulas, you can also calculate what is the variance of C. So all these designs that we have seen is these factorial designs, completely randomized designs, all these are kind of pre-cooked A constructions. So we are given recipes to compute properties of the matrix A, and then computers will solve the problem with least squares, and what we can do in advance is to design the properties of that matrix A that has to be inverted. Okay, so this would be all for the lecture, and in the next one we will see some examples of how to use a program to design all these kind of things.